Section 4.2, Null Spaces, Column Spaces, and Linear Transformations. The null space of an M by N matrix A, written as NUL or null A, is the set of all solutions to the homogeneous equation AX equals 0. In set notation, it looks like this. The null space of A is the set of all vectors X, where X is in the space Rn, and AX equals 0. So let's look at an example. Here we've got a matrix A, and it's a 3 by 3 square matrix, and a vector U. And we wanted to determine if our vector U belongs to the null space of A. So remember, the null space is the set of solutions to the homogeneous equation AX equals 0. So we want to see, does U satisfy the equation if I write it A times U equal 0? Is that going to work? So in order to test that, we need to compute A times U. So we're going to multiply our matrix A times our vector U. So here is my matrix A. Here's my vector U. And remember, when we multiply, we're going to go across and then down. So what I'm going to do is I'm going to multiply 5 times 5 plus 21 times negative 3 plus 19 times 2. And remember, this is a 3 by 3 and U was a 3 by 1, so our answer should be a 3 by 1, and we're wanting to get 0. So we've got 25 plus a negative 63 plus 38, and then for the second entry we have 65 plus a negative 69 plus 4, and then for our last entry, or third entry, we have 40 plus a negative 42 plus 2. So then we see that if we combine these, add them together, we will end up with all zeros, which is the 0 vector. And so then we know that U, our vector U, is in the null space of A. So it's pretty straightforward. If we're given a vector and we're given a matrix, to see if that vector's in the null space, we simply multiply the matrix times the vector and see if we get the 0 vector. And if we do, then we know it satisfies our homogeneous equation. Let's look at Theorem 2. The null space of an M by N matrix A is a subspace of our space Rn. Equivalently, the set of all solutions to a system AX equals 0 of M homogeneous linear equations in N unknowns is a subspace of Rn. So let's look at a proof. The null space of A is a subset of Rn, since A has n columns. So we must verify properties A, B, and C of our definition of a subspace. And remember, property A said that we need to show that the 0 vector is then in the null space of A, the 0 vector of Rn, of our original vector space. And so that's simply going to be a vector with n entries that are all zeros. So since we know that A times a vector X is equal to 0 for the null space, that it has to satisfy that equation, then 0 is in the null space of A. And the reason for this is we know, kind of from what we've looked at when we looked at homogeneous equations, that our equation AX equals 0 will always have at least the trivial solution. So we know that it always has the trivial solution, and what we looked at before was testing to see if we had a non-trivial solution. So we know that we will have the 0 vector of Rn in our null space. Now property B, we're checking to see if it's closed under vector addition. So if U and V are vectors in the null space of A, then we need to show that the sum of them is also in the null space of A. So since they're in the null space, then we know that they satisfy our homogeneous equation. Therefore, we know that if I take my matrix A times the sum of them, that the rules of matrices, I can split that up to being A times U plus A times V. And I just said that A times U was the 0 vector right here, and A times V is also the 0 vector. And so when I add two 0 vectors together, I will have 0. So then we see that U plus V is in the null space of A, and then so the null space of A is closed under vector addition. Our last property, property C, we're checking to see if the null space is closed under scalar multiplication. So if U is a vector in the null space of A and C is a scalar, we want to show that C times U is also in the null space of A. So we know with our rules of matrices that when I multiply my matrix A times C times U, that I can pull that scalar out and it's C times AU. But since U is in the null space of A, I know that A times U is the 0 vector. So I have C times 0, which is simply 0. So then I know that CU is in the null space of A, and it's closed under scalar multiplication. So since the properties A, B, and C hold, the null space of A is a subspace of Rn. In this example, we're going to let H be the set of all vectors in R4, or our space R4, so they are a set of vectors who have 4 entries, and their coordinates A, B, C, and D satisfy these two equations. We want to show that H is a subspace of R4. So we've just learned about the null space, and notice that we know that the coordinates of our vectors in R4 satisfy these two equations. So I can solve these to make them equal to 0, and I'll have A minus 2B plus 5C minus D equals 0, and then negative A minus B plus C equals 0. Just to reorder them, put them in the same order. So we see then that H is the set of all solutions of this system of homogeneous linear equations, since we were able to solve them and have them equal to 0. So we're talking now about the null space. So then we can now apply Theorem 2. So then we see by Theorem 2 that H is a subspace of R4, since H was the null space. There is no obvious relation between vectors in the null space of A and the entries in A. We say the null space of A is defined implicitly because it's defined by a condition that must be checked. We remember in the first example we had to multiply our matrix A by a vector to see if we got the 0 vector. No explicit list or description of the elements in null A is given when we do this. However, solving AX equals 0 yields an explicit description of the null space of A. So in this example, we want to find a spanning set for the null space of A where our matrix A is given here. Or, in other words, this kind of the same statement would be to find an explicit description of the null space of A, where we can actually see what the entries would have to be. So the first thing we need to do is to row reduce the augmented matrix corresponding to our homogeneous equation, AX equals 0. So here's our matrix A, and to make it the augmented matrix we're simply going to add a column of zeros on the end, and what we want to do is we want to row reduce it using, we can just use RREF to do that. And we end up with this matrix here. Now if you chose to leave off the column of zeros, you would just need to remember when you're row reducing that you're ending up with the coefficient matrix and it's not the augmented matrix until you add that column of zeros. So just keep that in mind. So the next step is to find the general solution in terms of our free variables. And you can see from our row reduced matrix that we have a pivot here in the first column and a pivot here then in the third column, and so we have free variables in column 2, 4, and 5. So I'm going to set up my vector x using x1, 2, 3, 4, and 5. And when we solve, we see that we get that x1 is then equal to negative 2x2 minus 13x4 minus 33x5. x2 is free, and then x3 is equal to 6x4 plus 15x5. x4 is free, and x5 is free. So now what I'll do is I'll factor out my x2s, x4s, and x5s, my free variables. So I have x2 then times a vector with negative 2, 1, and then 3 zeros, plus x4 times a vector with negative 13, 0, 6, 1, 0, plus x5 then times negative 33, 0, 15, 0, 1. And hopefully this is familiar. I'm kind of going through this. It's been a little while since we did the general solution. So if I call this vector here u, and I call this one v, and then call this one w, remember that this is the set of solutions to the homogeneous equation, and so this was a linear combination of these three vectors. So each linear combination of these three vectors, u, v, and w, is an element of the null space of A. So then we can say that the null space of A is equal to the span of the three vectors u, v, and w. So since then we have an explicit description, the general solution for the null space, which was the span of those three vectors, then the spanning set is the set U containing u, v, and w. This is a spanning set for the null space of A. So let's kind of sum this up. Some observations. Number one, the spanning set of the null space of A is found using the method that we just did in the last example. It is automatically linearly independent. And this is because the free variables are weights on the spanning vectors. So notice they use C1, C2, and C3, and this was my vector. This one we called U, this one we called V, and this one we called W. We know that in order for this equation to be true, where this is equal to 0, that our weights C1, C2, and C3 must be 0. So we see that this linear combination C1 times U plus C2 times V plus C3 times W can be the 0 vector only if the weights are all 0. So that tells us that it's automatically linearly independent. And then number 2, if the null space of A is not equal to the 0 vector, or when the null space of A contains non-zero vectors, then the number of vectors in the spanning set for the null space of A equals the number of free variables in AX equals 0. Now let's look at the column space. The column space of an n by n matrix A, written as COL-A, is the set of all linear combinations of the columns of A. So if A is equal to the set of vectors A1 through AN, then we can say that the column space of A is the span of those vectors that made up our matrix A. Theorem 3 says that the column space of an n by n matrix is a subspace of Rm. You may ask why. We want to recall Theorem 1 from the previous section, section 4.1. And this theorem said that if vectors v1 through vp are vectors in our space V, then the span of those vectors is a subspace of V. Since the column space is equal to the span, then we can say that the column space is also a subspace. Let's recall that if AX equals B, a vector B, then B is a linear combination of the columns of A. Therefore then, the column space of A is the set of all vectors B such that B satisfies that equation AX equal B for some x in Rn. The notation A times x for vectors in the column space of A also shows that the column space of A is the range of the linear transformation that maps x to A times x. In this example, we want to find a matrix A such that W is equal to the column space of A, where W is equal to this set here of vectors that satisfy, each entry satisfies these equations, where x and y are real numbers. So we can rewrite our space W as the set of all vectors where we have x times 1, 0, 1 plus y times the vector -2, 3, 1, where x and y are in the real numbers. So then we see that W is the span of my two vectors here, the span of the vector 1, 0, 1 and then -2, 3, 1. And that is then the definition of the column space of a matrix A, where A is then equal to this matrix that has those vectors as the columns. So this is then my matrix A that satisfies this. We can recall from Theorem 4 in section 1.4, remember this was an important theorem, that the columns of A span Rm if and only if the equation AX equal B has a solution for each B. So we can restate this as the column space of an m by n matrix A is all of Rm if and only if the equation AX equal B has a solution for each B in Rm. Let's look now at the contrast between the null space of A and the column space of A. In this example, we're going to let our matrix A be equal to this here, which is a 4 by 3. So I want to take note of that. M by n matrix, it's a 4 by 3. And remember that the column space of A is vectors that are in Rm, and the null space of A is vectors that are in Rn. So for the first question, the column space of A is a subspace of Rk where k is equal to 4, since it is sets that are in Rm and m is 4. Next question, the null space of A is a subspace of Rk where k is equal to 3, since these are in Rn and n was 3. And we're going to look at what the column space is and what the null space is in just a second, so this should make more sense. Right here we want to find a non-zero vector in the column space of A, and there are infinitely many possibilities. Remember that the column space of A is simply a linear combination of the columns of A. So here I've written the columns of A with spaces in front, and basically to be a linear combination means we're multiplying by some scalar each column and adding them together. And so we can let these scalars be anything we want, which is why there are infinitely many possibilities. The easiest one would be to have it be 1, 0, 0. So then we simply have the first column would be a non-zero vector in the column space of A. So each individual column is in the column space of A. The next thing we want to do is find a non-zero vector in the null space of A. So this is a little more involved. We need to actually solve the homogeneous equation AX equals 0 and then pick one solution. So here I've written the matrix A with a column of zeros, And what we want to do is row reduce it. So this is the matrix that we'll get. And we see then that x1 is equal to negative 2x2. x2 is free, and then x3 is just equal to 0. So what we can do is simply let x2 be equal to 1. Since it's free, it can be anything. And so then we would have that our vector x, which is just made up of our coefficients x1, x2, and x3, we would then have negative 2, 1, and 0 as a vector that's in the null space of A. And we could have let x2 be anything since it's free, so we'll have an infinite number. And so notice that we have 4 entries in our column vector. So it was in R4. And then we have 3 entries in our vector that's in the null space. So it was in R3. Now here we've laid out the differences between the two kind of side by side, and we can look at how these are defined. The first one we just looked at in the previous example. The null space is a subspace of Rn, column space is for Rm. The second one, the null space is implicitly defined, so you're going to have this condition that it has to satisfy. The column space is explicitly defined, so you know how to build vectors. They're a linear combination of our columns of A. It was easy to find those vectors in the column space, as we saw in the previous example, but you have to do a little work to find vectors in the null space. There is no obvious relation between the null space of A and the entries in A, but there is between the column space of A and the entries, since each column of A is in that column space. A vector V in the null space has the property that it satisfies AV equals 0, and then a typical vector in the column space of A has the property that our equation AX equal V is consistent. Number 6, given a specific vector V, it's easy to tell if V is in the null space of A. We just simply multiply our matrix times that vector and see if we get the 0 vector. But if we're given a specific vector V, it may take time to tell if it's in the column space. We're going to have to do row operations on our augmented matrix to see if it's consistent. The null space of A is equal to the 0 vector if and only if our equation AX equals 0 has only the trivial solution. The column space of A is equal to our space Rm if and only if our equation AX equal B has a solution for every B in Rm. And then I've included number 8 for both the null space and the column space. However, we have not studied one-to-one and onto, but for your own information, those two things are true as well. In this example, we want to determine whether each of the following sets is a vector space or provide a counterexample. So for part A, we have the set H, which is just a vector x and y that satisfies this equation x minus y equals 4. So we want to determine if it's a vector space. The easiest thing to do would be to look at our properties for subspace and look to see if the 0 vector is in here, and we know that it's not. If I choose values for x and y, there's no way that I can get them both to be 0 and satisfy my equation. So the 0 vector is not an H, and thus H is not a vector space. For my next example, I have the space V, which is the set of vectors x, y, z that satisfy these two equations. I can rewrite these two equations in this manner here and see that now if I call this my matrix A, then I multiply A by the vectors that are in V and I get the 0 vector. So then V is equal to the null space of A, where A is simply equal to this vector here, 1, negative 1, 0, 0, 1, 1. And since the null space of A is a subspace of R3, because this is a 2 by 3 matrix, then we know that V is a vector space. So when we looked at this to begin with, we saw that we had a set of equations equal to 0, so hopefully that would trigger something to make you look at the null space when you see that. And for this last set, we want to determine if S, with these entries satisfying those equations, where x, y, and z are real numbers, is a vector space, or provide a counterexample. One solution would be to rewrite my set of vectors, x plus y, 2x minus 3y, and then 3y, as a linear combination. So I'm going to pull out x, and I'll have 1, 2, 0, plus y times 1, negative 3, 3. So then what we have is that S, my set S, is equal to the span of those two vectors then, since it's a linear combination of them. So then therefore S is a vector space by Theorem 1 from section 4.1. Another solution, or basically another way to look at this solution, is we could have taken this here and said that S is then equal to the column space of A, where A is the matrix made up of those two vectors as the columns. And we know that the column space is a vector space, so then S is a vector space as well. And that may be a little easier way to look at it. The last thing we want to look at is the kernel and the range of a linear transformation. A linear transformation T from a vector space V into a vector space W is basically a rule that assigns to each vector x in V a unique vector T of x in W such that these two properties are satisfied. And this should look familiar from when we first looked at linear transformations back in chapter 1. The kernel, or the null space, of our transformation T is the set of all vectors u in V such that T of u, which is basically A times u, and that's equal to 0, which is then the 0 vector in W. And then the range of T is the set of all vectors in W of the form T of u, where u is in V. And here we kind of see a picture of this. So if T of x is equal to A times x, then the column space of A is the range of T. So the kernel is those specific vectors which give us the null space, where I'm multiplying A times those vectors and I get 0. And then the column space would be the range. Now you try. I want you to determine whether each of the following sets is a vector space, and if not, then I want you to provide a counterexample. Work on these and we'll discuss them in class.